This is our fourth and final part for day 3, and we want to do some graphical interpretations of definite integrals. So you should have looked at this graph and tried to roughly approximate the signed areas based on the definite integrals below. So the first one here is the integral from 1 to 2 of f of x dx. So our limits of integration are between 1 and 2, which means we're looking at the signed area just drawn in blue here. Start by making a definite guess that's too small and a definite guess that's too big, because each one of these squares is 1 by 1. They have 1 unit value, and there's 1, 2, 3 squares that are contained entirely under the curve, and once we pick 4 squares, we are too big. So we could say, if it was sufficiently accurate, that the definite integral between 1 and 2 is sort of sandwiched between 3 and 4. Now, if you want to make a better approximation, you can say, oh, look, this top square really, it's about half or 3/4. You don't have to be too terribly accurate. But I'm going to say that the definite integral from 1 to 2 of f of x dx is about 3.5. Okay, 3 3/4 would probably be a little bit better, but good enough for now. For the second problem, we have the definite integral from 4 to 6, and 4 starts about here. Notice that means we're looking at area below the x-axis, and that means the sign of this area is going to be negative. We can start with the broad over and under approximations again. So how many of these squares are contained entirely between our graph and the x-axis? I see 3, so that's an area of -3. And if I were to draw a box that contained everything, that would have an area, a signed area of -6. So which one's too small and which one's too big? Think about where -6 is compared to -3 on the number line. -3 is further to the right. It is the larger value. So we could sandwich our definite integral between -6 as the underestimate and -3 as the overestimate. All right, and then you can just sort of count and approximate to your heart's content, and I would say about -4.5. For the third one, the limits of integration are from 4 to 4. That means there's really no area to the rectangle you're drawing. It's just a line. Lines have no area. So that definite integral is only going to have a value, an exact value of 0. And then the integral from 0 to 6, you approximate the positive area above the curve and subtract off the negative area below the curve. I would say that's about 10 for the positive area, 5 for the negative area, so 10 minus 5, I get an answer of about 5. And for our final problem today, we might not be given a formula for our function, and we might not even be given a graph. We might just be told some facts about the function, and yet we can still deduce some answers for our definite integrals. So for this particular problem, f of x is a function that satisfies all 4 of the following bulleted statements. F of x is an even function. An even function is one that is symmetric across the y-axis. That means it has mirror symmetry across the y-axis. F of x is periodic with a period of pi. Well, if you're to draw that, so we only have to know what's going on between 0 and pi. If it's periodic with period pi, it should begin and end at the same place over that period. And whatever we draw has to be repeated every pi units. Now, we also want it to have mirror symmetry across the y-axis. So even though this may not be what the function is, I'm going to use it to represent whatever my function f of x is. So that's, a representation of some function that satisfies those first two facts. All right, then I'm given two definite integrals. I know that the integral from 0 to pi over 3 is 1, and the integral from 0 to pi of f of x dx is 3. So that tells me I know something about areas. So the area under the curve between 0 and pi is 3, and the area under the curve between 0 and pi over 3 is 1. That's all I have to work with. So how can we use these facts to come up with the definite integrals below? So look at the first one. It's the definite integral from pi over 3 to pi of f of x dx. Well, looking here, that's just the area under the curve between pi over 3 and pi. We can take the area between 0 and pi and subtract off what we got from 0 and pi over 3. So that's exactly what we'll do. We'll take the total area from 0 to pi and subtract off the area from 0 to pi over 3. 3 minus 1 is 2, so the integral from pi over 3 to pi is going to be 2. Second, the integral from negative pi over 3 to pi over 3. So that means we'd be starting over here. But remember, I have a reflectional symmetry, so whatever the area is over here to the left of the origin has to match the area to the right of the origin. Well, that was information we were given directly, so that tells us that the total area is going to be twice the area under the curve between 0 and pi over 3. So 2 times 1 is just 2. And that's lovely. Now, the integral from 0 to 4 pi, that's gone through 4 periods. We start at 0, we go to pi, we go to 2 pi, we go to 3 pi, and then we go to 4 pi. So it's just 4 times whatever the area is between 0 and pi. Well, the area between 0 and pi is 3, so the answer is going to be 12. And finally, this last one is a little weird. It's the area from pi to 0. So we're reading in the opposite direction. We usually have been doing this from left to right, and now we're going from right to left, and all that's going to do is change our sign. So, it's going to be the negative of the integral from 0 to pi. So if you want to flip the order of your limits of integration, you just take the negative of the definite integral. And that we already know, so the answer is going to be negative 3. All right, good work. You made it through day 3. I hope what you do before you get started on day 4 is try the problems on page 9 that's starting with the fundamental theorem of calculus in section 5.4. And I'm going to assume you have tried those, and we'll just start talking about those next time. Thanks for your flexibility, and I hope you are not being snowed out. Bye.